Hello, and welcome back to CS631 Advanced Programming in the Unix Environment. After we talked about inter-process communication in the last few videos, we are now looking to write an HTTP server as our group project. We will cover the basics of the HTTP protocol and class, but it's also useful to understand what it means to run a service continuously and in the background, which is something we typically mean when we speak of a server process. So in this video, we'll quickly discuss the details of such processes, which traditionally are referred to as daemon processes, named after the physics thought experiment Maxwell's Daemon, an agent running continually in the background performing certain tasks. The use of the word daemon to describe such a process also then led to the illustration of such a daemon, which in the early days of the Berkeley software distribution became the official mascot of BSD. As a fun side note, and an interesting little bit of Unix trivia, as I was preparing this video, I found out that the original BSD daemon was actually drawn by John Lasseter, formerly of Pixar Movies. He was working with engineers from the Computer Science Research Group at Berkeley at Lucasfilm, and rendering of his early short, Look So Junior, was handled by the CSRG at Berkeley. You see, Unix is everywhere. Now, the BSD daemon looks like this. But anyway, so daemon processes have a number of specific characteristics. They are designed to offer a specific service, and as such, live for a long time. That is, they may run for hours, days, weeks, or months uninterrupted, continuously. They are usually started automatically when the system comes up, and only terminate when the system is shut down. In addition, they are running in the background and have no controlling terminal. If you consider these properties, you'll quickly note that there are some pretty important implications. If you're designed to provide a specific service and you're running for a long time, then it'd be prudent to follow closely the Unix philosophy of doing one thing and one thing only. That is, you don't want to introduce complexity and keep things as simple as possible. You'll want to write your service carefully and avoid leaking resources, as running for a long time will eventually lead you to exhaust them otherwise. If you leak a file descriptor through some logic mistake on every request your server handles, that may not be a big issue when you're testing your service and run it for a few minutes. But if you're running for hours, days, or weeks, you eventually will run out of file descriptors this way. In this class, we've repeatedly noted the importance of writing code defensively and in a robust manner, aligning allocation of resources with freeing them, file descriptors, allocated memory, etc., to help you develop such clean coding habits. When your service runs, you need to consider the current working directory. This is not only important if you resolve path names relative to the current working directory, but also important as the current directory remains an open handle. If you, for example, have an open handle on a directory, then you cannot unmount the file system the directory is on. On many systems, you may have multiple file systems and may want to change them or otherwise have a need to unmount them without bringing the entire system down. But as long as a process keeps the handle open on a directory, you won't be able to do that. For this reason, it's usually a good idea for a daemon to change its current working directory to the root of the file system. Since you're running without a controlling terminal, there's very limited user interaction possible. For example, you can't interactively prompt the user for input. And neither can you print error messages or any other debugging information to standard error. That is, you have to consider some other mechanism of providing such messages, if they are indeed necessary or useful for the system administrator. So, being aware of these implications, how do we write a daemon? Normally, we start by clearing our environment to ensure our service cannot be influenced by anything we do not control. We fork off the parent process and have the parent process terminate. This leads to the child process being orphaned and then reaped by init, thus allowing it to run in the background and to be controlled by init. We usually set a desirable umask to ensure that any files created by our process, or any child process we might create, will get the right permissions. We then call setSyd to become the session leader of a new session, thereby losing any controlling terminal and allowing all of our processes to remain grouped in our process group and session as we described in week 7, video segment 2. We change the current working directory to a safe place, oftentimes the root directory, although you may also want to change it to a restricted directory elsewhere. Next, we close or redirect to dev null the standard file descriptors that would normally be connected with a controlling terminal, so that any other processes we create do not erroneously attempt to operate on standard in, standard out, or standard error. If you want to perform any logging, such as to send system messages to the system logs, or to keep track of all of our incoming HTTP requests, for example, then we need to open those file descriptors before we then finally enter the actual code of our server or service. Since there are many such services, or daemons, running on our Unix systems, we have developed a number of additional conventions surrounding the management of these services, the startup and termination, as well as their configuration. For example, we often want to avoid having more than one instance of our servers running, and so we often use a log file to protect against the second version starting up. We'll look at file and record logging in more detail in a future lecture, but sometimes it's sufficient to use a simple test for the existence of a file that our process creates, and then removes upon termination, usually via an exit handler. We also often want to be able to identify the primary process ID of the server, since many servers and services create many child processes. So for this reason, many daemons use a PID file to write the parent process ID too. As you can guess, you can oftentimes use this PID file as the log file, and refuse to start up if the PID file already exists, for example. Since we want our service to start up at system boot time, we usually provide a system startup file or script. These may differ based on the mechanism used to bootstrap the system, be that the BSD rc style startup, a System 5 derived init.d startup, or more recently using something like systemd. Since we have no way to interact with the user, our service often relies on a configuration file to read at startup to change its behavior as needed. By convention, these files are usually found in the etc directory and named after the service name. These configuration files may be changed at system runtime, so we want an easy way for the service to be restarted and reread its config file. For that, the convention is to have the service restart when it receives the hangup signal, sig_hub. The reason for this is that the hangup signal is something that under normal circumstances is only ever generated when a process loses its controlling terminal. But since our daemon doesn't have a controlling terminal, it cannot ever have such a signal sent to it, other than intentionally by the system administrator. So in a way, we hacked our way around the absence of a signal that means, yo, please restart and reread your config file, by overloading the hangup signal. Finally, as mentioned before, we need to ensure debugging information or warnings etc. are delivered to the system, and the standard way to accomplish this, in a service running in the background without a controlling terminal, is to use syslog. Here, let's take a look at what a typical daemon process might look and behave like. Here, under etc rc.d, we find the startup scripts of all the services which may be started when the system boots up. As you can tell, there's a whole bunch of them here, so let's see what's currently running. Here, in the output from proctree, we see dhcpd, sshd, powerd, inetd, postfix, cron, and syslog_d. Let's take a look at syslog. Here, in syslog_d.c, we see the initial setup, where we change our root, set the appropriate group ID and user ID, and then make a call to the daemon library function. Hey look, that's pretty neat. We have a function that does all the heavy lifting for us. It creates a daemon process running in the background, closing any file descriptors and changing the working directory for us. One thing to note here is that calling daemon changes your process ID, since you're forking, as we mentioned before. So what does this daemon library function look like? Let's jump into the source. Here we see exactly what we had outlined before. We fork, let the parent exit and the now orphaned and reaped by init child continue. We call setSit, chdir, and redirect the standard file descriptors. After that, we are proper daemon. So we can now write our PID file and begin the actual functionality. So what does a typical startup script look like? Here, etc rc.d syslog_d looks like so. We provide a command name, a PID file, and a config file. Let's look at the PID file. Looks like syslog.d currently has process ID 2179, which PS can confirm for us. Let's take a look at the configuration file, etc syslog.conf, and add a new directive to log local messages to a new file. With this change to the config file, we need to have the daemon stop and restart, rereading the config file for the change to take effect. So we can simply kill PID 2179 and then start the executable ourselves. Note that the command immediately and silently returns to us. syslog.d now runs as a daemon in the background with process ID 2410. And yes, it dutifully and correctly noted its PID in its PID file. Good. To verify that it reread the configuration file, let's send a log message of the given facility into syslog and observe it being logged to the file we had specified. There it is. Okay, let's remove this change again. But now, to restart, we can try to use the system startup scripts. Look at that! The script is smart enough to check if syslog.d is already running, and by inspecting the PID file, it can give you an idea which process you may want to check. So we can run rc.d syslog.d restart, which will then terminate process 2410 and restart it, leading to a new process running in the background. Okay, I hope this was a useful demonstration to show how a typical daemon, the syslog daemon in this case, runs in the background. You should next try to see what happens when you send the hub signal to the daemon after you've made a change to the configuration, as well as try to trace how the rc script restarts the daemon in detail. There are a few other interesting and related links and systems. Begin your exploration with these manual pages and links here. In our next videos, we'll begin a deep dive of how shared libraries in the executable and linkable format work. Until then, thanks for watching. Cheers!